entrance and beyond. This is day 8 of my DSA series. Today I will be covering question number 973, that is k closest points to the origin. It's a question of medium difficulty, so let's dive right in. So the question states, given an array points where points of I is equal to xi, yi, represents a point on the xy plane and an integer k, return the k closest points to the origin, that is 0, 0. The distance between 2 points on the xy plane is the Euclidean distance I root over bracket x1 minus x2 to the whole square plus bracket y1 minus y2 to the whole square, and that is pretty much it. You may return the answer in any order. The answer is guaranteed to be unique except for the order that it is in. So the question is quite simple. We are basically given an array points, and basically points of I has two values. It has basically x coordinate and its y coordinate, which basically represent its coordinate on the xy plane, and we are given an integer k. What we have to do is we have to return the k closest points to origin. That is pretty much all that we have to do. So let's look at the test cases just so that things become more clear. So our first test case is points is equal to 1, 3, minus 2, 2. K is equal to 1 in this case. So output is minus 2, 2. So we can see that they're basically drawn out the points over here. And what they have showed in the explanation, the distance between 1 and 3 from the origin is square root of 10. The distance between minus 2 and 2 from the origin is square root of 8. And since square root of 8 is less than square root of 10, what we can say is minus 2, 2 is closer to the origin, and k is equal to 1. So we have to return the element that is closest to the origin. So we're just going to return that element, so minus 2, 2. Let's look at the second test case. So the second test case says points is equal to 3, 3, 5, minus 1, minus 2, 4. K is equal to 2. So we can basically compute distance, and we end up finding that 3, 3 and minus 2, 4 are the closest points to the origin. So we're just going to return that answer. We're going to return that answer. So yeah, that is pretty much all that we have to do, and then we are given the constraint. So let's copy a test case and understand how we can solve this question. So let's copy this test case and let's try to solve it. So what is the brute force approach that you can think about? So the brute force approach is quite simple. You can say that we're gonna have a vector that's gonna store pairs. So the first value of the pair would basically be distance from origin of a point, and the second value would be the index. And then what we could do is we can basically sort by distance. Once we have sorted by distance, we can simply return the first k element, store that somewhere, and we would have our answer. So how exactly would that work? So suppose we're gonna have this data structure. Now this is basically a vector. And each vector is suppose going to store 2 points. It's going to store a pair of points. So this is a vector, right? So what we're going to do is we're going to look at the first element. We're going to call a helper function, find the distance of this from the origin. So if we do, it's going to end up being root 18. So what we're going to do is we're going to store it in the array root 18. We're going to store its index. Then we go to the next element. We calculate distance again. It's going to be root 26. Root 26 is the distance. Its index is 1. Now we're going to go to the last element, calculate distance. It's going to be root 20, root 20, root 20, 2. Now we're going to basically sort according to index. So sort according to the first element, sorry. So if we sort according to the first element, what's going to happen? This is going to stay where it is. This 26 is going to move over here. Sorry, just a second. So what's going to happen is this is basically what's going to happen after sorting. So boom, we're going to select this element, move it out. Then this 26 would go to the end, and then 20 would come over here. And then in our final answer, we know we have to return the k closest. So the k closest would be this element and this element. So we're just going to get the index from it. So index 3, 3 minus 2, 4, and that is pretty much it. So this approach, if we look at the time complexity, it's basically big O of the time complexity over here is going to end up being big O of log n log n, because we're sorting. And this is pretty much our first approach. So I just explained the brute force approach. You can go on ahead and code it. It's simple. You store the distance, store the index, then you can directly store it in C++. It's going to sort according to the first element. And then what we have to do is we basically have to get the first k elements, store that somewhere, and that is pretty much it. So this was our first approach, but there definitely has to be some better approach that takes less time than n log n time. So what could be that approach? So whenever you encounter a problem where they say k smallest or k closest or anything related to k, at the end of the day, in most cases, you can end up using a data structure known as a heap. If you don't have a clear idea about a heap, it's basically a data structure that stores the maximum value at the top or the minimum value at the top, and you can simply remove that element. So that is pretty much it. It is basically essentially a binary tree in the backend. So you can research a bit about it, but I'll show a basic visualization. So I'll use this tool over here. So thank you for University of California for creating this visualization tool. So it's going to be a minimum heap. So in a minimum heap, as the name suggests, minimum. So the element at the top of the heap is always going to be minimum, and we can just remove that element. So over here, insertion takes login time, and the same thing happens for deletion because it's basically a binary tree, and we know in a binary tree, login time is required for basically sorting things. Because at the end of the day, in the minimum heap, we are sorting the nodes, so that's why it takes login time. And if that still didn't make sense, please do watch some videos regarding minimum heap. I won't go into the details about heaps in this video. I could do that in future videos. For now, I'm just going to use the concept that you need. So I'll just show visualization. So you basically get 5,000, it gets added. Then suppose we have 6,000. 6,000, it gets added over here. Then we can have something like a 5,500. 5,500, it's going to get added. And the main property about a heap is the child, in a minimum heap, the child is always less than parent. Or sorry, the child is always greater than parent, and in a maximum heap, the opposite condition would be there. Now if we remove the colors, 5,000 will get removed, and now the smallest element will be at the top. 5,500, we could remove that smallest, now we'll be left with 600. That is pretty much it, and hopefully understood the visualization of minimum heap. In maximum heap, it would kind of be the same. The only difference that would be present is that the top would have the maximum value. That is pretty much it. That is pretty much it. So like in this case, let's make this tree way smaller. Let's remove some of the elements. Let's see. Okay, like in a maximum heap, we can say that suppose we enter the max, we have to remove the maximum element, extract it. So since it's a max heap, we get the maximum element. And now what happens is the maximum, current maximum element, or the maximum element that is left, it becomes 79. So that is pretty much what is happening. So this basically I did array mode, but now suppose if we extract the maximum element, what's going to happen? 79 is going to get replaced, and our new maximum would become 65. So you can see that now 65 is at the top, and that is pretty much all that you need to know about a max heap. So in the max heap, the top element is basically the maximum value, and the minimum heap, the top element is the minimum value, and when you extract something, you basically get the top value. So how can we end up using this in our question? So viewers could basically say, what if we use a minimum heap, we add all the elements into the minimum heap, and we just remove the top k elements? That would be our answer. So that again is a good approach, but that would again take n log n time, because at the end of the day, we as I mentioned, for insertion, log n time is required, and same for deletion or removal, log n time is required. And if we do that for n elements, it's going to end up being an n log n approach. So we must basically refine that approach so that we only have k elements in our heap. So you can think about it. Why do we even need n elements in our heap? Why can't we just keep k elements in our heap? Why can't we just do that? If we just have k elements, the time for insertion would be log k, and time for deletion again would be log k. And if we do insertion for n elements, it's going to end up being n log k, due to the fact that our heap never exceeds a size of k. So how can we do that? So it might sound counterintuitive, but I'm going to basically create a maximum heap. I'm going to create a maximum heap. So let's take this case. I'm going to create a maximum heap, and in the heap, what I'm going to store is I'm basically going to store a pair. The first value would basically be distance, and the second value would be index. And I'm going to use a maximum heap. And I'm going to ensure that the size of the maximum heap is always less than k. If the size of the maximum heap becomes greater than k, we can remove the largest element. Now, this is why we are using a maximum heap. Because if we remove the largest element and we're left with k elements, they ought to be the k smallest elements, because the largest element has been removed. So let's try to do that. So what we're going to do is we're going to basically start off with 3, 3. The maximum heap is basically empty, or its size is less than k. We check both the conditions. That is true. So what are we going to do? We're going to take the distance that we got over here. We're just going to copy that and boom, bang it in and put it right in over here. So this is our first node. Now we basically move ahead. Now we are going to look at this 5 comma minus 1. We calculate its distance. Now size is basically uh, size is less than k, so we're going to clearly add the element. And now what we're going to do is we're going to add another node. So let's copy this node. I'm going to paste it somewhere. uh, so yep, something like this. This is suppose our new node that was added. So I'm just adding it to a random location. That the location doesn't really matter. What I'm going to do now, I'm going to copy this entire thing. Since we have this, this is going to go right into this node. Now we still have k element. Now what are we going to do for -2 and 4? This already has k element. So logically thinking, we could say that we won't insert it. We're just going to remove the largest. So the largest at this point of time would be 20 comma 2. So this would go on the top. Yep, since it is a max heap, this was a minimum heap example. So since it is a maximum heap, this would basically go on the top. Okay, so what's going to happen, this entire thing is going to move to the top. And we can say that this entire thing, or this entire thing, would move to the bottom. So let's say we can take this, and take this entire shape, move it down, and this is what we have. Now, using logic, we could say that we basically won't add this, and we're going to check if this element is greater than the element to be added. We would remove this, else we won't. But from the code aspect, what we're going to do is we're going to add, and then after adding, we're going to check if the size is greater than k. If it is, we're going to remove the maximum. So in this case, something similar would happen. We're first going to end up adding this. So we're going to take this, add it, then we're going to take this, add it, and then this would be the element at the top. Now side exceeds 2, so we're just going to remove the top element. So as you can see, we have the k smallest now elements now, and we just then use the index and store our output somewhere. So this is going to end up taking big O of log k time. So this is going to end up taking big O of log k for each insertion, because our heap is of max its of size k, and then for n elements and log k. This is a time, so this is definitely better since k is less than n mode in most cases. So this is a better approach. Now let's try to code it up. So here I am in my IDE. So I basically created a helper function that would be calculating the distance of a point from the origin. Since we know it's the origin, so we can say distance would basically be equal to power of x squared, so x to the power 2 plus y to the power 2, and we can take the root, but we don't even need to take the root, we can directly compare the values. And a better thing to do is we could just directly do x squared plus y squared, so we don't even need power function since we're just doing x squared plus y squared. And we don't need to find the root, because like I mentioned, if the value inside the root is larger, the distance would be larger. So like I mentioned, we're going to use a minimum heap or maximum heap, sorry. So for priority queue, it's going to be declared. It's going to be a pair int comma int, because we're storing both the distance and its index. And this is going to be labeled as maximum heap. And now what do? We basically have to return the output in vector of vector int format, so let that be output. We're going to traverse through points. So for int I is equal to 0, I is less than points dot size, I plus plus. That is pretty much it. I is equal to 0, I is less than point dot size, I plus plus. We're going to push things into the max heap. So max heap dot push. What are we pushing? We're pushing a pair. So pair will basically be distance. In distance, we're going to pass points of I comma 0, points of I comma 1, that would be the y coordinate, and then we're passing the index. So after doing all of this, we have basically pushed in the value, and after pushing, we're checking if the size exceeds k. So if max heap dot size, if it is in fact greater than k, what are we going to do? We're going to do max heap dot pop out the top element or pop the maximum element out. We've constructed our map heap, and now max heap, sorry. And while our max heap is not empty, what do we have to do? We have to add our output in vector. So you can say output dot push back. Now what do we have to push back? We have to push back the value, correct? So what are we going to do? We're going to do max heap. We're going to do points. So points will basically give us this 2D array that we had. So points of max heap dot top dot second. So dot top would basically give this the pair having distance, the first value being distance and the second value being index. So we're going to use dot second to get the index, and we're just basically now getting the value at a specific index, and then we can do max heap dot pop, and now we can end up returning output, and this should work perfectly fine. And it takes n log k time. It takes n log k time, so there will be a comma right here. So let's see. Now this is how you write it. Now this is how things work out. We missed a comma. We basically put I within this. Don't have to do that. So now when we run the code, you see that we got the answer. So hopefully things did make sense to me, and it makes sense to you as well. To me, it was really clear. Initially, I did face some doubts in this question as well, but once you read the theory about max heap, I think things will become way more clear. And hopefully, this video did help. So thank you so much.